Hello, welcome. We're going to talk about the Clausius-Clapeyron equation. Now, this is an equation that was discovered by two independent scientists just working in different laboratories, and so they didn't know who to name it after. It's pretty cool. So let me show you exactly what we know about the vapor pressure of a gas versus temperature. Now, we know that the vapor pressure is going to depend on two things. First, it depends on temperature. If you have a higher temperature, you're going to have a higher vapor pressure. If you have a lower temperature, you have a lower pressure. Now, we're not just talking about a gas by itself. We're talking about maybe a liquid that's in a container that's enclosed. Okay, so there's gas vapor, and then there's liquid, right, that can vaporize and form vapors. And that's at equilibrium. All right. Now, we also know that it depends on the intermolecular forces. If a liquid has very high intermolecular forces, it's actually going to have a lower pressure. And if it has low intermolecular force, it's going to have a high pressure. And why is that opposite? Well, remember that intermolecular forces are kind of like a stickiness that holds molecules together. So if molecules are really sticky and they have a high intermolecular force, then they're not going to evaporate or vaporize as well to produce pressure. Okay, so let's take a look at some vapor pressure graphs. We have ethyl ether in red, ethyl alcohol in blue, and then water in, sorry, there's four different graphs here. Got a little confused. But anyway, take a look at these vapor pressure graphs, and we have several different substances here. And they all have logarithmic curves that describe the pressure as a function of temperature. Now, if we take a look here at the normal pressure, okay, which would be, in our case, 1 atmosphere or 760 millimeters of mercury, we could take a look and we can see that the boiling point of ethyl ether is 35 degrees Celsius, okay? This other substance here, ethyl alcohol, has a boiling point of 78 degrees Celsius, okay? So what conclusion we can draw here is that ethyl alcohol has higher intermolecular forces than ethyl ether because its boiling point is higher. Now let's do a reality check and see if that's the case. Here's ethyl alcohol. If we look at the Lewis structure, we can see that it can exhibit hydrogen bonding, which is the strongest IMF, and it's going to cause this molecule to have higher intermolecular forces, be sticky, and therefore have a low vapor pressure. Now, if we look at ethyl ether, it is a polar molecule, so it has dipole-dipole forces, and of course, both of these molecules have London dispersion forces, but ethyl ether is not a hydrogen bonding solvent, so it's not going to have as high intermolecular forces. So ethyl ether is more free to volatilize, and that's why its vapor pressure is higher at normal temperature, and its boiling point is lower, okay? Lower boiling point. All right. Ethyl ether, by the way, boils at 35 degrees Celsius. So if you're kind of running a fever, you could probably put a test tube containing ethyl ether on your forehead and make it boil right in your on your forehead. All right, here's water. I want to explain how the vapor pressure of water also depends on temperature. We've got this curve here, right? So we all have memorized that the boiling point of water is 100 degrees Celsius. That's not always the case. It's dependent on the pressure. So at normal pressure, or 760 millimeters of mercury, yes, the boiling point of water is 100 degrees Celsius. But if we lower the pressure of water, maybe 526 millimeters of mercury, say we go onto the top of a really high mountain somewhere, the boiling point of water is actually going to drop to 90 degrees Celsius, for example, in this case. And we can also increase the pressure, say, for example, in a boiler or a steam engine or a pressure cooker, and pressurize the gases in there. If the pressure is 905 millimeters of mercury, it turns out that the boiling point of water is going to be raised, and it's going to be 105 degrees Celsius, okay? Now, I wanted to bring your attention to table 9.2 in the OpenStax textbook. We sometimes call this the steam table, and it lists the different temperatures and pressures for water. Now, what's really cool is that even at minus 10 degrees Celsius, an ice cube is going to have some sort of vapor pressure, only due to the possibility that ice can sublime. But if we take a look at ice cold liquid water at 0 degrees Celsius, it's going to have a very small pressure of 4.6 millimeters of mercury. And of course, at 100 degrees Celsius, it's going to have a vapor pressure of much higher, 760 millimeters of mercury. Okay. The boiling point of a substance is defined as when the vapor pressure is equal to the atmospheric pressure. So here in the atmosphere where I'm standing in the lab, 500 feet above sea level or so, the vapor pressure in this room, if it's 760 millimeters of mercury, the water is going to have to reach a temperature of 100 degrees Celsius to match that pressure, okay? All right, so let's talk about the Clausius-Clapeyron equation. It's pretty crazy looking. It's somewhat intimidating here. We have a natural log of ratio of two pressures, and that's equal to the heat of vaporization over the constant R times the difference in kelvins, by the way, of two different temperatures, the reciprocals, okay? And so there are two ways to calculate the thing you want to calculate, okay? You can use that equation, you can use math, the formula and algebra, make sure you show your units, do all the manipulations and get the number you need. Or I'll show you a neat little trick to use a Clausius-Clapeyron calculator. And you definitely want to use this if you just need the number, you're doing some engineering calculations, and or you just need the answer, okay? So first off, we can calculate any variable we want. Usually we're interested in calculating the heat of vaporizations, and I think it's rather interesting that you just need two temperatures and two pressures, and you can get the heat of vaporization of any liquid you want without really doing any thermochemistry or measuring temperature changes and heat flow and all that kind of stuff, okay? So, but you can also solve for temperature or pressure. Let's look at our first example. We want to use the Clausius-Clapeyron equation to calculate the heat of vaporization. And let's say the substance has a pressure of 17.5 millimeters of mercury at 20 C, that's around room temperature, and it has a higher vapor pressure of 149.4 millimeters of mercury at 60 degrees Celsius. So, of course, we want to write down our Clausius-Clapeyron equation, but first, be careful. Convert everything to Kelvin. So add 273.15 to all of the Kelvin numbers to get your temperatures in Celsius, all right? And go ahead and plug those into your equation here, all right? And we'll do this stepwise here. On the left-hand side, you can see how the millimeters of mercury are going to cancel. You want to take that ratio and hit the LN button on your calculator. Don't forget that. And I've done the math over there with the temperatures, okay? The kelvins cancel here in yellow. And then just do algebra as you normally would to calculate what the delta H is. The heat of vaporization is 43,000 joules, or you can divide by 1,000 and report it in kilojoules per mole. Usually somebody's going to ask you for the heat of vaporization in kilojoules per mole or calories per gram or something like that. I normally go with kilojoules per mole. All right, let's take a look at example 2. Calculate the heat of vaporization for a substance having an initial pressure of 0.655 atmospheres at 71.90 degrees Celsius and a final pressure of 24.1 atmospheres at a much higher temperature of 198.33 degrees Celsius. All right, let me show you a screenshot of me doing that using the Clausius-Clapeyron equation calculator. I'll give you the link in the description below. We've got some nice ads here to distract our attention, and we have the initial temperature. Let's see, it's in degrees Celsius, and we type in 71.90. Okay, the final temperature is T2, which is 198.33 degrees Celsius. And the initial pressure is in atmospheres. What the heck, technical? Okay, so standard atmospheres is what we want, ATM. Let me go ahead and do that for both. So the initial pressure is 0.655, that's P1. And the final pressure is 24.1 atmospheres, okay? And we normally display this in kilojoules per mole, so the answer there is 38.57. Okay, so you can see how using the calculator is much simpler there's the link. Check the video description below so you can just click on it. Heat of vaporization here for this substance, I believe, was isopropyl alcohol, pure 2-propanol, and it's 38.6 kilojoules per mole. So remember, the heat of vaporizations for substances is going to always be a positive number because it takes energy to convert liquids to their gaseous forms. Thanks for watching. Please like, please subscribe, and have a great day, everybody.